Hi everyone, we are Team 18 and we will be presenting our analysis and redesign of the push reel lawnmower. The push reel mower was made for greater cut consistency, which is essential for sports fields. The wheel's torque is transferred to the gear to spin the blade reel to cut grass. The height of the grass can also be adjusted too. The reel mower has mostly been replaced by powered mowers, but are popular to smaller lawns and work well to maintain golf course greens. They are chosen for their quietness, precision cut, size, lack of pollution, and ease of maintenance. We can estimate 100,000 units sold globally. Here is the exploded view of the product showing the parts of the original design. On this slide is the flash diagram. We have one main functional branch that allows the mower to cut the grass. The functional component mapping matrix shows 6 components are associated with push mower, resist jamming, enable portability, and reduce noise, revealing redundancies within the existing design. The handle cap and handle base only support one function, representing a potential part reduction. The handle rod and connection brackets realize 3 common functions and therefore should be considered for reduction. The two customer groups have different demands, mainly the size of the cut area that the mower cuts. Using the component mapping matrix, we can identify the platform and module parts. As seen in this slide, we can see the different modules providing the different functions showed in the fast diagram. In the assembly sequence, it does not change any of the platform to module parts.
To make the platform selection for DFA manual, the function component mapping matrix was consulted, which showed that there was a lot of functional overlap and hence an opportunity for part consolidation of the handle, handle cap, handle base, and rod. When considering these parts and their fasteners, they have the highest combined assembly time. The handle and rod are also high cost per the quad chart, making them good candidates for the redesign, while the handle cap and base are low functional importance and cost, and thus potential candidates for part reduction. For the module selection, the connection brackets were chosen as they have one of the highest assembly times, as well as high functional importance and cost per the quad chart. Prior to DFA manual, the current design was baselined at an assembly efficiency of 19% and total assembly time of 284.38 seconds. Prior to DFA, the handle, handle cap, handle base, rod, as well as the 3 nuts and 3 screws necessary to assemble these parts required an assembly time of 83.19 seconds. Via DFA, the team was able to optimize the handle and rod assembly time down to 8 seconds by reducing part counts, removing the handle cap and handle base, and combining the handle and rod into one part, eliminating all 6 of the fasteners, which was enabled by part consolidation and the implementation of the snap fits. This redesign does not majorly impact part function, but it does increase material and manufacturing costs due to the rod becoming ABS. Prior to DFA, the connection brackets and their 2 nuts and screws required an assembly time of 58.76 seconds. By applying DFA, the team was able to reduce the assembly time to 46.16 seconds. This was achieved by reducing part counts, combining the 2 brackets into one, implementation of the snap fit interfaces, increased part symmetry, and the added features for easy insertion. This redesign does not majorly impact part function, but it does increase material and manufacturing costs due to the material added when consolidating parts and increase in required machining steps. Overall, redesigning the selected platform and module parts resulted in an improved assembly efficiency of 24.4% and an assembly time of 196.59 seconds, which was an 87.79 second decrease.
In order to perform our design for automated assembly, we chose the wheel frame subassembly. This was selected due to several parts having high functional importance, as well as many parts here being small enough to be used effectively for automated assembly. The pieces chosen for automated assembly were the gear cover, the roller adjustments, the pinion gear, and the screw. When performing the automated assembly cost, we did find that before the design for automated assembly, the overall cost to perform an automated assembly of these parts would be $49.92. After performing the design for automated assembly optimization, we found there were a few updates we could make. Reduce part variety by using the same screw for the roller adjustment and the frame. We could add features to facilitate orientation for the roller adjustment and the frame. We could add features for easy insertion by chamfering the holes for easy insert of the fastener, and provide locating features within the gear cover to assist with the assembly of a fastener. Overall, this would not have a change on the part function, but there would be a slight increase in cost due to extra machining steps. Overall, the assembly cost after the design for automated assembly was $45.46, a $4.46 savings.
Here we are looking at the process selection for the handle and rod. The function of this combined part is to push the mower, steer the mower, and enable portability. The critical dimensions of this rod all surround the snap features, and a standard tolerance of 0.5 millimeters should allow a clip engagement of 1 millimeters to the mating component, and this is the design requirement for our mower. The section thickness of this part is 3 millimeters. Based on the process selection for the handle and rod, we found that machining, injection molding, and compression molding all would be suitable manufacturing processes for this part. Our team elected to move forward with injection molding in order to economically reach our 100,000 batch size. For the process selection of the connection bracket, the functions surround the connection bracket are to push the mower, steer the mower, enable portability, and adjust cut width. The critical dimensions of the connection bracket also surround the slots that will connect to the snap features on the handle. A standard tolerance of 0.5 millimeters will also allow the 1 millimeter of clip engagement, which is our mower requirement, and the section thickness of this part is 4.5 millimeters. Based on the process selection analysis, we found that sheet metal and machining were both suitable manufacturing processes for this part, but we elected to move forward with sheet metal for its simplicity.
Handle and rod assembly is injection molded using a flat parting plane with a complex parting surface. The part has a maximum wall thickness of 3.02 millimeters and a tolerance of plus or minus 0.5 millimeters, which results in a volume of 1072.34 centimeters cubed. For our analysis, we used an opaque standard finish. The initial cost per part is $4.98. DfM Pro analysis made the following suggestions: increase the draft angle, minimize the wall thickness and make it uniform, and avoid undercuts. After implementing these suggestions, our part now has a volume of 929.4 centimeters cubed and a uniform wall thickness of 2.5 millimeters. We also added a draft angle to make the core easier to remove and moved the location of the snap fit features to eliminate the undercut. This results in a new cost per part of $4.30, a savings of 68 cents, with no effect on function or assembly cost.
For the DfM with sheet metal of our connection bracket, we use the assumptions and parameters from the bullets shown. After running our design for sheet metal calculations, we came to a total cost of $2.29. When running the quotes from hubs, extrapolating to our volume rate of 100,000 units, and taking 80% of that derived value, our estimated cost is approximately $6.74 per part. DfM Pro analysis for the connection bracket gave us the following recommendations. The minimum width of a slot needs to be optimized. The cutout distance to the part edge and also to the bend distance need to also be fixed. Our DfM Pro optimizations did not change any of the bulleted assumptions and parameters. However, applying DFSM rules 7, 8, and 11 did increase our manually derived cost estimate by 5 cents. The part function and assembly cost remain unchanged by this improved design. However, for volume manufacturing, there is no cost increase when getting our estimates from hubs. In fact, the improved DfM marginally reduces the lower volume estimates we received. In terms of our product service system, we aim to reduce our negative impact on the environment and improve our customer experience. To do this, we will offer service contracts that allow the customers to receive free blade replacements after sending in their old ones. Additionally, we could further improve customer experience by adding an odometer and tracking the mileage on leaderboards, offering discounted services and products for the highest usage customers. To conclude and critique our design for manual assembly gave us the largest gain in value by reducing the total assembly time by 87.79 seconds. Design for automated assembly gave us an additional $4.46 in savings, and our design for manufacturing on the connection bracket and handle rod yielded a total of 63 cents in savings. While the overall design has improved in terms of both time and cost, with additional time and resources, our design would benefit from further DFA and DFM optimizations on other parts as well. Additionally, we would look for ways to reduce our cost on the blades, as those are our most expensive part.